In this video, we're going to go over several examples of the ratio test. So first we're going to start with the sum from n equals 1 to infinity of negative 2 raised to the nth power over n squared. Now technically, because we do have a negative number raised to the nth power, we could technically apply the alternating series test for this. However, we're going to go with the ratio test. So a ratio test says that we are supposed to set up the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Now, that is just a fancy way of saying set up a fraction where the numerator is this expression with the n's replaced with n plus 1's, and the denominator is simply this expression. So this will be the limit as n approaches infinity of, this will be a rather large fraction, since it's going to guarantee that there are fractions inside of our fraction. Yo, dog, I heard you like fractions. So a sub n plus 1 will look like this expression, negative 2 raised to the n plus 1 over n plus 1 quantity squared. Your denominator is going to be negative 2 raised to the nth power over n squared, same as the original expression. In the majority of these examples that we see, you're frequently going to have a fraction divided by another fraction. So my recommendation is going to be, rather than division by a fraction, change it to multiplication by the reciprocal of that fraction. So we'll take the denominator, we'll flip it, and we'll change it to multiplication. Now, of course, this is a test for absolute convergence, so we want to make sure that the absolute value bars are around the whole thing. Now, other recommendation that I'm going to give for you is that certain of these terms that you see in here came from the same part of the original expression. For example, the negative 2 to the n plus 1 and the negative 2 to the n are basically the same kind of beast, whereas n squared and n plus 1 squared also came from the same place. My recommendation is going to be to group those things together. So in the numerator, take the negative 2 to the n plus 1 and group it with this denominator. Since everything here is multiplied, it's okay if we switch it up a little bit. Then the n squared over n plus 1 quantity squared, those should be grouped together as well. Next, we're going to do a little bit of algebra to simplify everything. When you have the same base and they're both raised to powers, you can subtract those powers. So this will be the limit as n approaches infinity of negative 2 raised to the power of n plus 1 minus n. And when you have a square divided by a square, you are allowed to factor that square out. Now over here for the first part, we have the limit as n goes to infinity of, this will be negative 2 raised to the first power. And then this in here, I'm actually going to perform an algebraic manipulation inside of the parentheses. And the manipulation that I'm going to do is divide top and bottom by n. I recognize that as n goes out to infinity, this is going to wind up being infinity over infinity, so either L'Hopital's rule or an algebraic manipulation is going to be the way to go. So I'll put it all together. We have the absolute value of negative 2 times, this will be 1 over 1 plus 1 over n squared. Now as n goes to infinity, this 1 over n is going to go to 0, meaning that this term will wind up being 1 squared. This is negative 2, but we take an absolute value. We wind up with 2. Now, the ratio test says that if we get a number that's bigger than 1, we are allowed to draw a conclusion. And the conclusion is, therefore, by the ratio test, the series sum from n equals 1 to infinity of negative 2 raised to the n power over n squared diverges. If we wind up getting a number that is greater than 1, this is going to be a divergent series. Less than 1 it converges, equal to 1 we need to try another test. So with that in mind, let's take a look at another example. Here we have the sum from n equals 1 to infinity of n raised to the 10th power over negative 10 raised to the n plus 1th power. N plus first? Is that, I don't know. Words are hard. English is hard, man. So once again, we're going to set up the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Same as what we did for the last one, we're going to replace all of the n's with an n plus 1, and we'll be taking the limit as n goes to infinity of very large fraction. N to the 10th will be n plus 1 raised to the 10th power over, now this one will have an n plus 1 plus 1, so negative 10 raised to the n plus 2th power, n plus 2nd, n plus 2th. No, I'm not feeling it. Denominator, same thing, n to the 10th power over negative 10 raised to the n plus 1th power. Still inside absolute values as we are testing for absolute convergence. We will manipulate this one the same way as what we did for the last one, which is express this as first fraction, and then we'll multiply by the thing that we're dividing by, or multiply by the reciprocal of that. So negative 10 raised to the n plus 1 power over n to the 10th power. Now, like we did for the last one, we can reorder this so that the terms that look like each other can be grouped together. So negative 10 raised to the n plus 1, I want to group that one with the negative 10 raised to the n plus 2. They seem like they would go together well. And this is going to be times n plus 1 to the 10th power over n to the 10th power. I want to group those together as well. Now, for this term right here, as n goes out to infinity, we're going to wind up getting infinity over infinity. Now, if you want to use L'Hopital's rule 10 times on this problem, you certainly can. My sincere recommendation, though, is don't. That's a terrible idea, especially when there are algebraic manipulations that can work much better. If I take negative 10 to the n plus 1th power and negative 10 to the n plus 2th power, then what I'm going to do is perform a little algebraic manipulation on the denominator and say that this is the same as saying negative 10 to the 1st power times negative 10 raised to the n plus 1th power. The alternative would be to simply say subtract the exponents and we'll wind up with negative 1. Either of those will work. Now we're going to perform the same algebraic manipulation with this power as what we did on the previous problem and just factor out that 10th power. So the first fraction that we have in here will wind up being 1 over negative 10. Then, if I distribute this n to both terms here, this will be n over n plus 1 over n, and that's being raised to the 10th power. Now, if I allow n to go out to infinity, this term will, very similarly to the other one, go to 0, and we'll have 1 raised to the 10th power. Absolute value of negative 10 is going to give us 10 in the denominator. Important conclusion that we can draw is that the number that we got was, in fact, less than 1. Therefore, by the ratio test, we are allowed to draw a conclusion. The series, sum from n equals 1 to infinity of n to the 10th power over negative 10 raised to the n plus 1th power, is absolutely convergent. Bless you, sweetie. Sorry, my cat just sneezed. I should probably clean. Oh well. So, now that we've seen one successful conclusion where it diverges and one successful conclusion where it absolutely converges, let's take a look at the following example. This time we're going to try out the sum from n equals 1 to infinity of square root of n over n squared plus 4. Unlike the last two examples, this one doesn't actually contain an alternator. It does not contain a negative raised to an nth power. So if it converges, it's automatically absolutely convergent. That said, we're going to try the ratio test anyway, just to see what happens. So limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So set up a nice big fraction, limit as n approaches infinity of absolute value of. Replace all the n's with an n plus 1. This will be the square root of n plus 1 over n plus 1 quantity squared plus 4. All over a sub n, which is just the original expression. Make that a little longer. So limit as n goes to infinity of, We'll do the same thing for this as what we've done on the last couple problems and say we'll change that to multiplication by the reciprocal, like so, times multiplication by the reciprocal. Gut. So with those things in mind, I want to group the similar terms with each other. Limit as n goes to infinity of absolute value of. Square roots should go together. So square root of n plus 1 over the square root of n. And then for the next one, let's put the n squared plus 4 with the n plus 1 squared plus 4. Now, as far as algebraic manipulations for this one are concerned, I'm going to take a slightly different approach than on the previous problem because this looks like it needs to be expanded. For a square root divided by a square root, no problem there. We'll turn it into one nice big square root, n plus 1 over n, times. For this one, we're going to expand. This will be n squared plus 4 over. This will expand into n squared plus 2n plus 1. Then with the plus 4 at the end, that'll be n squared plus 2n plus 5. The reason I wanted to expand this is so that we can avoid having to use L'Hopital's rule by dividing the top and bottom by n squared. So limit as n goes to infinity of. Similar algebraic manipulations is what we've seen on the previous problems. We'll distribute this n from the denominator to the two terms in the numerator, n over n plus 1 over n, times. And for this, we'll get 1 plus 4 over n squared. And in the denominator, this will be 1 plus 2 over n plus 5 over n squared. Now we are ready to let n go to infinity. Anything with an n in the denominator is going to go to 0. So this goes to 0, this goes to 0, this goes to 0, and this goes to 0. Meaning that we're left with the square root of 1 times 1 over 1, which is 1. Now the reason that this is unfortunate news is we are allowed to draw no conclusion. When the ratio test gives a final result of 1, the ratio test has failed to give you a conclusion. Now, for the record, the last two worked out great because we had some exponentials in them. This one contains no exponentials. It contains only powers. That's when the root test tends to be less effective, is when you have powers rather than exponentials. For a successful test, if you're interested in trying this out, try a limit comparison test. When we think about what happens to this sequence when n gets really, really big, that plus 4 doesn't really have an influence anymore. You wind up essentially with the square root of n over n squared, which would be equal to n to the 1/2 power divided by n squared, which is the same as saying 1 over n to the 3/2 power. Now because of that, I would say limit compared to this p-series, and this p-series, for the record, is convergent. Do try that out. It'll be a good one. One more example. We haven't seen any with factorials yet, so let's try one out with a factorial. This will be the sum from n equals 1 to infinity of n factorial over 100 raised to the nth power. Now we're interested in setting up an expression that is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. For the record, though, everything in here is already positive, so if it's if it's convergent, that means it's absolutely convergent as well. So, limit as n goes to infinity of big ol' fraction. We'll replace all the n's with an n plus 1. This will be n plus 1 factorial over 100 raised to the n plus 1 power. Those are big numbers. All over n factorial over 100 raised to the nth power. Same algebra as what we've seen on the last couple of examples. Since we're dividing by a fraction, we are going to flip and multiply. These first couple steps of algebra are pretty consistent when it comes to the ratio test, which is set up your expression, change it to flip and multiply, then regroup so that things that look like each other are around each other. Specifically the factorials, I want them in the same fraction. N plus 1 factorial over n factorial. And the 100s raised to a power, I want those together as well. Now what we're going to do is expand both the factorial as well as the exponential. And by expanded, I mean a factorial says multiply by every integer from n plus 1 all the way down to 1. Which means that means the same thing as saying take n plus 1 times every integer from n on down to 1. This technique is referred to as expanding the factorial, and it works really well when you have another factorial that's around. Take whichever one is bigger and expand that particular factorial. We're also going to take the bigger power of 100 and expand it as well. When we say 100 to the n plus 1th power, that's like saying 100 to the first power times 100 to the nth power. If I were to multiply these two bases together, I'd be adding the exponent, so 1 plus n. Doing it in reverse is called expanding the exponential. Now, when I simplify the things that I'm able to simplify, specifically the n factorials will cancel and the 100 to the nth powers will cancel. The only thing that's left up top is n plus 1. The only thing left in the denominator is 100. Despite the fact that that 100 is a very big number, it pales in comparison to when n goes out to infinity. As a result, this limit tends toward infinity. And something that you should probably know about infinity is that infinity is greater than 1. The ratio test allows us to draw a conclusion due to the fact that infinity does happen to be bigger than 1. So therefore, by the ratio test, the series sum n equals 1 to infinity of n factorial divided by 100 to the nth power diverges. Yeah, that'll teach infinity to be bigger than 1. Actually, maybe that'll teach 1 to be smaller than infinity.